Okay, so then for the lectures, so we have 3 more lectures, so today, Monday, and Wednesday. And I'm going to switch up the format for the last 3 lectures since you all don't have a problem set covering this material. What we're going to, and the problems in this area are really fun. So what we're going to do is I'm going to, each of these 3 days, I'm going to start by with a lecture that's like maybe half the class. So today we're going to just state and prove a theorem. And then I've written some exercises for you all to work on for the second half of class that involve that theorem. So for the second half of class, I'll just post the problems on the screen, and that you can also find them on Canvas. They're under files, and they're called like lecture exercises or something. And you'll just break up into groups and work on the problems, and I'll come around and answer any questions that come up. Does that sound good? Okay, so let's prove the theorem. So we spent the last class talking about polynomial irreducibility. So now it will be finally kind of like revealed why we care about polynomial irreducibility. So we'll prove the following theorem. So let F be a field. And P of X be a polynomial with coefficients over F. Then P of X, the ideal generated by P of X, is maximal if and only if P of X is irreducible over F. Okay, does this statement make sense? Are there any questions? So let me just note quickly that we had a previous theorem that said an ideal was maximal if and only if f of x mod p of x is a field. So this theorem, once we prove it, is going to be kind of a launching point for a study of fields, because now we know how to make a lot of examples of fields. Just anytime you have an irreducible polynomial, you can look at the corresponding field. And so this is like really going to be the focus of the next few lectures, and the exercises going along with them is like what can we learn about these fields. Okay, so let's prove the theorem. So we have to prove both directions, so I'll start with the forwards direction. So for that, we'll suppose that P of X is maximal. Okay, so then we can write, or we can suppose that P of X is equal to G of X times H of X for some G and H in F of X. So let's suppose that this is some factorization of P over F. Okay, then what do we need to show? We need to show that no matter what, one of these two is a unit, right? So let me also just remark that throughout this, we can assume that P is non-zero since it generates a maximal ideal. It's not, the zero ideal isn't maximal, so P of x is not 0. Okay, so then from this factorization, we can say that the ideal generated by P of x is contained in the ideal generated by G of x. Okay, so why is that? The ideal generated by G of x contains this element, G of x times H of x, which is equal to P of x. So anything in here can be written as an element of the form something times G of x. And furthermore, this is contained in the ring of polynomials with coefficients in F. And since P of x is a maximal ideal, we have that the ideal generated by G of x is either equal to the ideal generated by P of x, or it's equal to the entire polynomial ring. So we either have that P of x equals G of x, or this is equal to fx. Okay, does it make sense so far? So what happens in both cases? I think the second case is a little bit easier, so let's start with that one. So if gx is equal to fx, then 1 is an element of the ideal generated by gx. So that means that 1 is equal to g of x times some other polynomial. Let's see, what letters haven't I used? F of x. Which means then that g of x is a unit. Which is what we wanted to show, right? So in this case, we're done. Are there questions about that part? Okay, then let's turn to the other case. So if these two are equal, then g of x is actually already contained in the ideal generated by p of x. So there exists a polynomial. Let's see, now I'm really running out of letters. I'll call it qx. There's a polynomial qx such that g of x is equal to px times qx. Okay, are we good up to this point? But then we also know that p of x itself is equal to g of x times h of x. So we can rewrite this whole equation as g of x is equal to g of x, h of x, q of x. And since we're in an integral domain, we have cancellation. So this means that 1 is equal to h of x, q of x. Which then means that, so looking back, what did we actually want to show? We wanted to show that either g or h was a unit. So that means that h is a unit. Okay, so what did we do? We showed that whenever we factor this polynomial p of x, we find that one of these is a unit. And so that means that there's no like proper factorizations of p of x. So we can conclude that p of x is irreducible, which is what we wanted to prove. Okay, are there any questions about this half of the proof before we go into the other half? Okay, then let's do the other direction. So for the other direction, we're going to want to assume that px is irreducible and prove that the ideal it generates is maximal. Okay, so to prove that this generates a maximal ideal, we're going to want to assume that there's some ideal that contains it, and then show that that ideal either has to equal the ideal generated by p of x, or it has to equal the full polynomial ring. So let's let I be an ideal in fx such that the ideal generated by px is contained in I, and of course that's contained in fx. Okay, so we want to show that one of these inclusions must actually be an equality. Okay, so here we have to kind of use a trick. So we know, we proved a couple classes ago, that this ring is a principal ideal domain. So that means that we can write I as being generated by some polynomial. So we know, or we can write I as equal to the ideal generated by g of x for some polynomial g of x. Okay, so that means that we can write, since we have an inclusion here, we can write P as an element of this ideal. So we can write P of x as g of x times something, so some h of x. Okay, so where should we go from here? Yeah. Yeah, so since P is irreducible, we know that either g of x or h of x has to be a unit. So let's see what happens in either case. Okay, if g of x is the unit, then that means that I is equal to the ideal generated by 1, which is the entire ring. And then if h is the unit, then that means that I is actually equal to the ideal generated by P of x. Right, so why is that? So like, let's suppose we have, or let's just show that g of x is in p of x. So why is that? So g of x is equal to p of x over this unit h of x. So since it's a unit, we know we can invert it. And so that shows that g of x is an element of, this should be the ideal generated by p of x. We know that g of x is in the ideal generated by p of x, and so that means that I is equal to the ideal generated by p of x. Okay, so in either of these cases, we have that either I is equal to the ideal generated by p of x or I is equal to f of x. So we can conclude that p of x, the ideal generated by p of x, is a maximal ideal. Okay, and that finishes both directions of the proof. Does someone have a question? Yeah.
Why does it imply that one of them is a unit?
Why does that what?
Why does it imply that one of them is a unit?
Because p of x is irreducible. So if you ever write a factorization like this, then one of these has to be a unit. Yeah. Other question?
So is the only unit
A unit would be anything that's invertible. So it could also just be an element of the field that's not zero. So you're talking about like for this part?
Yeah.
So, okay, yeah. So if g of x is a unit, then g of x times 1 over g of x, so whatever that is, then this is in the ideal I, but this is equal to 1. Yeah. Yeah, so anytime you have a unit in your ideal, that just means that the ideal is equal to the entire ring. Because you can always show that 1 is in there. Other questions about this proof? Yeah.
Can you explain the right side a little bit? Like what p of x divided by the unit h of x implies that I is equal to the principal?
Yeah, okay, so why is this true? So I claim that it's enough to show that g of x is contained in there. So why is that true? Well, I can write g of x as p of x times something, where that something is the multiplicative inverse of h of x. Yeah. Other questions? Okay, so if there's no other questions, then let's switch over to doing the lecture exercises. So I'm going to change the screen. So here are the exercises today. If you want to look at all of them, you can find them. They're posted on Canvas. So let's break up into groups. You can just chat with the people who are sitting around you or the people you normally talk to about exercises. And if you have a question, just raise your hand and I'll come over and answer it.